Okay, so we're going to start section 8.1. At the very last section of chapter 7.6, I think, we were testing means and comparing means from two different samples. But the samples had to be what we call match pair samples, where it was the same individuals usually before and after some treatment is applied. And that's neat because you're able to test a treatment on a group. But again, this limitation that it has to be the same people just eliminates a whole lot of studies that you probably would need to do still, depending on what you're doing. So, like for instance, I've talked about COVID a lot because it's relevant right now. You can't have the same people being tested where some of them are on a COVID vaccine. Sorry, you test people before you have the same people tested before and after they go on the COVID vaccine. That just won't work because the before vaccine group, they're going to be living in different conditions than the after vaccine people. That would be the same people after vaccine. And the reason why the conditions change is just because the world is constantly changing. There are rises and falls with the rate of infection out there. And as we know, back in the winter, it was really bad. And if the after group is put out there and the infection rates aren't as high, then they're just different conditions. So what you really want are two groups that are living through the same conditions at the same moment in time with the same sort of level of infection that's going on at the time. So they have to be different people. And I think there's just lots of cases where we need to look at different groups that are independent samples, not paired up the way we talked about. So everything that follows in chapter 8 assumes that we're going to be working with two independent samples, still thinking of it as a control group and a treatment group, but they're just different people now. The samples don't need to be the same size, but we're still going to be looking at differences between the two samples. And we're going to be subtracting, if we're working with proportions, and there's only two numbers we really study in statistics. They are proportions or means from samples. So if you're looking at two proportions, you're going to be doing a test on the difference between two population proportions. And if you're looking at means, you're going to look at the difference between two population means just to see if they're significantly different. Okay. But I think we can go ahead and jump on in now. This lesson will basically develop the formula for our test statistics. It'll be Z when we work with proportions and T when we work with means, because we're no longer going to pretend that we know the population standard deviations. We'll just work with sample standard deviations. Okay, so I think we can go ahead and begin here. So it says here we lay foundations for hypothesis tests that compare two population parameters, either means or proportions. So the first test we'll study is the difference between two proportions. When we estimate a population proportion P, we use the sample proportion P hat. The mean of sample proportions, mu P hat, is P, the population proportion. So the mean of sample proportions is the population proportion. And the standard error you've seen repeatedly, it's the square root of PQ over N. Okay, now remember, standard errors or standard deviations don't have cool properties. Variances have cool properties. Okay, so we'll be looking at the variance of sample proportions. And the goal here is to look at differences between sample proportions to see how different they are. And remember, sample proportions are approximately normal if NP is at least 10 and NQ is at least 10. Okay, those will continue to be important. We remember that differences, and again, we're going toward differences. Differences are normal as long as the two populations that you're subtracting are normal. Okay, so if we want to compare two population proportions, P1 and P2, using sample proportions, P hat 1 and P hat 2, from independent samples, we subtract them, P1 minus P2. The difference between the population proportions is estimated using the difference between sample proportions, p hat 1 minus p hat 2. When we want to determine if such a difference is significant, we need to compute a z-score, but this requires a mean and a standard error. Okay, and we know lots of things about means and variances, and that's how we'll get at it. So we know the difference, the mean difference is the difference between two means. So the mean of p hat 1 minus p hat 2 is the expected value of p hat 1 minus p hat 2, which is the expected value of p hat 1 minus the expected value of p hat 2. So the mean of the difference is the difference of the means. And the mean of p hat 1, we have the statement up here. The mean of a sample proportion is the population proportion. Okay, well, we have two sample proportions here. I should have put subscripts. There's a p hat 1 and a p hat 2. Okay, and the mean of these are the population proportions, p1 minus p2. Okay, so this is the mean of differences between sample proportions. It's the difference between the population proportions. Okay, now to do the variance, variances are a little different. The variance of differences is the sum of the individual variances. So when you look at the variance of p hat 1 minus p hat 2, it's going to be the sum of the variances, the variance of p hat 1 plus the variance of p hat 2. Variances add even when you subtract the variables. Okay. The variance of a sample proportion looks like this, PQ over N, but now there's two of them. So we're adding them together. There's going to be a P1, Q1 over N1, and then the other one's going to be a P2, Q2 over N2. Okay, and the standard error is just the square root of the variance. So standard error or standard deviation would be the square root of what we just did. So P1 Q1 over N1 plus P2 Q2 over N2, like that. If we take a z-score of a difference between two sample proportions, this would look like this. So you have the z-score, which is the difference, p hat 1 minus p hat 2, minus the mean of differences over the standard error of differences. That's how you take a z-score. So again, the difference is p hat 1 minus p hat 2, and minus the mean difference, we said was the difference of the means, and the means are p1 and p2. So the mean difference is p1 minus p2. Over the standard error, which we just figured out, it's the square root of this mess here, which I think I'm just going to copy and paste. Like that. So that's how you're going to take a z-score of a difference between two sample proportions. And it will be, I need the normality criteria. So this will be normal. And I'll just remind you, the difference between two population variables are normal if the individual populations are normal. So I need both distributions to be normal. So I'm going to be saying this, N1, P1 greater than or equal to 10. N1, Q1 greater than or equal to 10. Yeah, but it needs to be true for both of them. N2, P2 greater than or equal to 10. N2, Q2 greater than or equal to 10. Okay, so you're going to have a lot to check on these to demonstrate that the distribution will be normal. Differences are normal if the populations you're subtracting are normal. So they both have to be normal. Okay, any questions with all that? So this is our test statistic for the next lesson. Any questions? There's another one here for the difference between two means. And it's almost the same sentences. I'm going to kind of glide through this a little more quickly. The population mean is mu. The sample mean is x bar. The mean of sample means is the population mean, mu. And the standard error or standard deviation is sigma x bar, which is sigma over the square root of n. And you've seen that in the denominator of your t statistics, but sigma is changed to s there. Now you square it to get the variance. That's sigma squared over n. And sample means are approximately normal when your sample sizes are bigger than 30 or you're sampling from a normal population. Now we want to take two sample means and two population means. The population means are mu1 and mu2. The sample means will be x bar 1 and x bar 2. Okay. If we want to compare the sample means, we subtract them. X bar 1 minus x bar 2. The difference between the population means is estimated using the difference between the sample means. Okay. When we want to determine if such a difference is significant, we compute a z-score, but this requires a mean and a standard error. It'll later turn into a t-score. So the mean of differences is the expected value of differences, and the expected value of differences is the difference between the expected values. But the expected value of a sample mean is the population mean. So for the first one, it's mu1, and for the second one, it's mu2. So the mean of differences is the difference of the means. That's what this says. But the variance of differences is the sum of variances. So variance of x bar 1 minus x bar 2 will be var of x bar 1 plus var of x bar 2. Like that. The variance of a sample mean is up above. It's sigma squared over n, but there's two of them, and we're adding them. So there will be a sigma 1 squared over n1 plus a sigma 2 square over n2. Okay? And then, of course, the standard deviation is the square root of the variance. Notice I'm using sigma 1, not S1, and sigma 2, not S2. And because I'm using population standard deviations, the standard score of this is not the t, it's the z-score. T only comes in when we use sample standard deviations in place of population standard deviations. Okay. So the z-score takes the statistic, which is x bar 1 minus x bar 2. It subtracts the mean. The mean of differences is the difference of the means, mu1 minus mu2, over the standard error, which we figured out up above. Like that. And it says z, which stands for the normal distribution, and I'll say this is normal. If both the sample sizes are bigger than 30 or the populations are normal. So N1 could be bigger, should be bigger than 30, and N2 should be bigger than 30. If either one of those doesn't work, then the respective population should be normal. I'll just say, or the populations are normal. Okay, any questions there? I should add that when the sigma, let's just say wins S1 and S2 are substituted for sigma 1 and sigma 2. Mute that. Okay, so when those are substituted, the statistic becomes T. So you'll see that not in, in a couple of sections. We're not going to do this one until I guess it's 8.3. So we're going to try and squeeze in 8.2. We're getting really good at this, so I think we could probably do an example. All right. So we're going to look at section 8.2 real quickly. This one is actually just like previous sections. The only real thing that's happened here is that our test statistic is going to involve two proportions from two different samples. So let's go ahead and read through the problem, and I'll just walk you through. We already know from the previous section what our test statistic is going to look like. We're going to have to alter this a little bit, but it will be a Z statistic. I don't know what the P1 and the Q1 and the P2 and the Q2 are, so we're going to have to use sample data for that. Go ahead and read through this. It says this, I don't know if this is depressing or not, a little depressing. It says, in this lesson, we studied a hypothesis test comparing two population proportions. Here's an example. The following example are based on a study from UNICEF, which is it's United Nations organization that monitors the health and safety of children, I think. From a random sample of 825 school-age girls from all over the world, 693 are allowed to attend school. In a random sample of 861 school-aged boys, again, from all over the world, random selections, 750 are allowed to attend school. So we're going to test the claim at 2% significance. Don't ask me why I picked 2%. That the proportion of girls worldwide who are allowed to attend school is lower than the proportion for boys. Okay, any questions? Okay, so we're going to need data. So we're going to need to gather we're going to need a p hat 1, which will be like x1 over n1. And this will just be the first one they give us. Okay. P hat 2 will be the second one. So x2 over n2. The conditions are complicated. Normally, I'm going to erase what I'm about to write. Actually, you can look back. Okay, I said it's normal if N1 times P1 is at least 10, N1 times Q1 is at least 10. You're not going to be able to verify this. Just as a reminder, we don't know what P1 and P2 are. N1 times P hat 1, just to remind you, is N1. P hat 1 is X1 over N1. Those cancel, okay? That's just X1, which is the number of successes. Okay, so all that is to say, we're going to, instead of checking N1, P1, we're just going to say at least 10 successes in the sample, because that's approximately what N1, P1 will be using N1, P1 hat. P1 hat is the estimate of P1. Okay, N1, you do the math, N1 times Q1 with a hat is the number of failures. Okay, so when we go back to this, the check here will be nothing more complicated, at least 10 successes and 10 failures. In each sample. Okay, so let's go ahead and do this real quick. So p hat 1, this is going to be the girls. It's 693 out of 825. Okay, so check that. So I get 0.84 exactly. So these data, and this is like 10 years old, just to let you know. I don't know what's happened in the last 10 years. It seems like the world's gotten crazier, but p hat 2 for the boys. 750 out of 861. So what percentage of boys are going to school? And rounding this, I got 87%, 0.871. Okay, so that's a 3 percentage point difference, which might be within the margin for error. Okay, any questions? I don't know. 3 percentage point is usually a margin for error with 1,000 in your sample. This is a little more complicated than that because we have 2 samples now. Okay, any questions? Okay, so we do need to check the boys and the girls for successes. So for the girls, there were 693 successes. Of course, that's greater than or equal to 10. How many failures? This would be 825 minus 693. So that's obviously going to be greater than 10, but we're jumping through hoops. So that's 132 fails. Also, that's plenty, greater than or equal to 10. For the boys, we continue. 750 were allowed to go to school. So that's greater than or equal to 10. The fails are 861 minus 750. And obviously, again, this will be bigger than 10. It's 111. So yeah, we're good. So I'll just put a big check mark there to say I checked. Any questions? Okay, so in general, when we do our null hypothesis, it'll be P1 equals P2. There's no difference in the 2 populations. The alternative, you have to pick. So you can do P1 less than P2, P1 greater than P2, or P1 not equal to P2. And again, this is for left tail, right tail, or 2-tail tests. I'll go ahead and write that in one more time. So this is for the left tail test. This is right tail. And the last one is for the 2-tailed test. Okay, any questions? That null hypothesis is always this. It doesn't have to be, but that's just how we did it. So null hypothesis, we just say P1 is equal to P2. Now, I think the claim was that girls, that it's a lower proportion of girls who are allowed to attend school. Right here, the proportion of girls who go to school, allowed to go to school, is lower than the proportion for boys. See the lower there? So we should say P1 is less than P2. And that makes this a left tail test. Okay, any questions? Okay, now I'm going to put the z-score back down here, but it's going to get altered, unfortunately. So the z-score that we worked out in the last section was p hat 1 minus p hat 2. I've got both of those, minus p1 minus p2. Okay, the null hypothesis was going to say that the difference is 0, So I think I'll just, but, again, we're claiming that these are the same number in the null hypothesis. So that'll be 0 when you subtract them. It'll always be 0. So I'll just leave that there. And then the standard error, I'm going to write it and then I'm going to have to change it. Okay, so here's the standard error. This one doesn't say, this one actually requires the values of P1 and P2. And so that's the problem with it. Sorry, P1, Q1 over N1 plus P2, Q2 over N2. There, that's the formula. And why can't you compute that? Well, again, P1 needs a value to do it. Up here, I didn't need P1 or P2 because we're saying the difference is 0. So we're just going to put a 0 there. But here, I actually need the value of P1 and the value of P2 to continue. The most natural thing is to use P hat 1 and P hat 2 for those, because they are the estimates. And that's not a bad idea, but a better idea pays attention to the fact that we're supposed to believe that assume the null hypothesis is true. Null hypothesis says those two guys are supposed to be the same number. P1 and P2 are supposed to be the same, but P hat 1 and P hat 2 are different. So if they're the same, what value is closest to the population proportion that's shared by both populations? What you do is you pool the two sample proportions. So we're going to combine, since the population is supposed to be the same, let's combine the samples. Okay, so P bar is what we're going to use instead of P1 and P2. I'm going to put in a P bar, and why not have a Q bar on both of these? Okay, where P bar is supposed to be that common proportion that's common to both. I'll mix the total number of children, not just boys or girls, but we're mixing them together now. The total number of children allowed to go to school divided by the total number of children in my samples combined. Okay, and we're going to call this the pooled proportion. Okay, so the number of boys allowed to go to, girls is 693 plus number of boys 750 over total number of children, 825 girls plus 861 boys. Okay, so let's see what that is.
I got 0.856.
So you get, that's just so fast. Yeah, that's what I got too, 0.856. And while you're at it, Q bar is going to be 1 minus P bar, of course. These are complements. So 1 minus 0.856, what's that? 0.1, is it 144?
Yeah.
Thanks. Okay, so now we're using a pool, what this thing's called a pooled proportion, because we pooled the samples together. Okay. Now we can compute our Z statistics. So the P hat 1 is up above, that's the 0.84. Minus P hat 2, that's the 0.871. And just to humor us, I'll put minus a 0 up there. And then the denominator is going to be a monstrosity. So I'm going to try and write really small. Okay, so this is going to get a 0.856 times 0.144. And you're using it for both variances. N1 is 825. Because we're assuming the population proportions are equal, we use that same numerator on both of them. But the denominators are different. All right, see if you can do that. You think you're so smart? Really easy to do this in Desmos. Actually, I think I'll just show that just for the heck of it. What do I got going here? I'm going to delete that last bit. Okay, so first of all, I type a slash for a fraction and then 0.84 minus 0.871. I won't bother subtracting 0. Then the square root is in the toolbar. Let's click on that. And then a slash for the first fraction, which is 0.856 times 0.8144. I'm going to stretch this out a little bigger here. There you go. And then down arrow to the denominator, 825. And then press the right arrow once. Do not leave the square root or you'll get the wrong answer. Got to make sure you're still in the square root. Plus a slash for the next fraction. Same numerator, 0.856 times 0.144. Different denominator. This time it's 861. And you should hopefully get what I got, negative 1.81. What do you guys think?
Yeah, I got that.
Oh, thank goodness. Okay, good. So that seems sort of significant, not highly significant. You're still counting standard errors. Basically, you're saying these two sample proportions is are 1.81 standard errors apart. And the girls is 1.81 standard errors below the boys. It seems significant. We've seen more significant things. Okay, but let's go ahead and get our critical value next. So this is the bottom row of table A2. This one's a left tail test, I think we said. Okay, so here's our critical value on the Z distribution. If you go to the bottom row of table A2, where the degrees of freedom are just large, those are Z scores. Our alpha is, I have no idea. This one says 2%, which is just plain weird. 0.02, and it's a one-tail test. And I'm looking to see if we have that table here. No, we don't. So the bad news is you're going to have to go back to the chapter 7 notes to see the table. Okay, so I'm popping back real quick to the chapter 7 stuff. Down at the bottom, this is our table. Okay, so 0.02, one tail. Huh. Right there it is. Bottom row, where the Z-scores are, all the way down to that guy, which I can't see. It says 2.054. So that's statistical significance on this one, which is a little bit of a disappointment. I always like to reject my null hypotheses. And this one telling us that our statistic is not significant on this one. 2.054. So let me put that into the notes real quick here. Okay, so remember it's a negative, it's a left tail test. You want to make this negative. So negative 2.054. So the alpha is the area of the left tail here on the critical value. So I'll go ahead and do that. That's our alpha of 0.02. Okay, so we're saying that our z statistic, that the z equals negative 1.81. This is not in the tail. So based on our rule, it's not statistically significant. But it would have been with a different level of significance. You'll see that with the p-value. Okay. So remember, it's a z distribution, normal. Our z statistic was negative 1.81. So I'll put that maybe here. And we'll look up our p-value. This is going to be table A1. Z-scores, p-values are in table A1. And that's the one we started with. So go down to negative 1.8 and out to 0.01 to get that p-value. This should be pretty precise. Table A1 is good enough for most scenarios. Again, I'm going to have to pop back to previous lesson to see that table. I'm going to the end of chapter 7 here. And here's table A1. Okay, and we want to remember it's negative 1.81 here. So here's negative 1.8 and 0.01. Let me zoom in on that now. Table A1 is the Z probabilities. Table A3 is the T probabilities. So this is coming out to be 0.0351. And remember, our level of significance is 0.02, so that's not going to pass. Take 0.0351. Let me go back. Okay, any questions? Again, it's Z distribution because our statistic is called Z. So the name of the statistic tells you what table you should use. Table A2 says the normal Z distribution on it. Okay, and I think we're ready to wrap this up here. So it says, make a conclusion. The rule is, as always, when the p-value is less than the level of significance, you reject the null hypothesis. Otherwise, you don't. So our p-value is 0.0351, which is bigger than our 0.02 level of significance, our alpha, which means if it's larger, we fail to reject the null hypothesis, which means we don't support the alternative, H1. H1 had said that the proportion is lower for girls. Okay, and that's actually nice to know. It's a worldwide statistic. I think if you looked country by country, you'd get some things that really stand out. But if you're looking across the world, then you're mixing all the countries together, and it's harder to see that. So we'll just make a little conclusion here. We can't support the claim that it's lower for girls. So the data do not support the claim that the proportion of girls worldwide who are allowed to attend school is lower than the proportion for boys. Okay, guys. Just to let you know, I think I'll wrap that up here, but just to let you know. Okay, so this is section 8.3. This one's on hypothesis tests comparing two population means. At this point, we're going to assume that the population standard deviations are unknown. And whenever that happens, you get this additional variability that forces a t-distribution for probabilities. Okay. Any questions about that? Okay, so otherwise, I mean, we already know what the test statistic will look like. We set it up as a Z statistic in section 8.1, but we'll call it T and replace with two sample standard deviations in there. Let's go ahead and jump on into the problem. Again, section 8.3. In this lesson, we study hypothesis tests that compare two population means. Here's an example. Child psychologists are starting to believe that when children watch too much TV, their sleep duration, number of hours they sleep a night, decreases. Seems obvious. Researchers gathered a random sample of 14 children, that's a little small, who watched TV for 3 hours or more on a given day. Their mean sleep duration for this sample was 6.78 hours, that's an average, with the standard deviation of 0.63 hours, that's just too little sleep. Another random sample was gathered for 18 children who watched TV for less than 3 hours on a given day, and their mean sleep duration for the sample was 7.44 hours, which is not an hour more, but it's approaching an hour more, with a standard deviation of 1.05 hours. Researchers have some evidence that these samples are drawn from normal populations. Okay, that's good, because our sample sizes are small. We have to test the claim at 4% significance level that children who watch more than 3 hours of sleep get less sleep than children who watch less than 3 hours of sleep. I watch less than 3 hours of TV, sorry. Okay, so this is all pretty straightforward. Just like all the others, we need to gather our sample data. So we'll need an X bar 1, an S1, and an N1. Those will just be whichever mean and standard deviation are given first. Okay, we're going to need an X bar 2, an S2, and an N2. We're going to need alpha. Okay, and we need to check that N1 is bigger than 30, N2 is bigger than 30, or the populations are normal. Okay, to this point, does anybody have any questions about where we're going with this? Sample size is bigger than 30, guarantee that sample means will be approximately normal in distribution. Okay. Well, we don't have that, but let's go ahead and write down what we do have. X bar 1 is, let's see, it's the first mean, which was 6.78 hours. Okay. And S1 is the first standard deviation, which was 0.63 hours. N1 is the sample size, so that's 14 kids. Okay, this is less than 30. X bar 2, for the second sample, we see 7.44 hours sleep on average. S2, that one was a standard deviation of 1.05 hours. N2, the sample size was 18 children. Again, too small. Okay, so let's go ahead and for our check. Oops. Let's go ahead and say N1 are, and N2 are both less than 30. That's bad. But the populations are both normal. So that's all we need. Okay, any questions?
I got one just to make sure I'm caught up.
Go ahead.
The basic idea here is that we're going to take the difference. We're going to take the difference of these samples and see if they're equal to 0 or not.
The null hypothesis. Well, I mean, equal to it won't. Do you mean the difference of the sample means or the population means?
I mean the difference of the sample means. Is that like our goal here is to like our null hypothesis should, I guess that's the next question, so I might as well go into that. But
I'd say we want the sample mean, the null hypothesis will be that the population means are equal. And so the sample means would have to be significantly different to disprove that.
got it. Okay, yeah, that's well stated.
Okay. So then in general, the null hypothesis is always going to be mu1 equals mu2. Now, there are cases where you wouldn't do that. You might say, you know, like I talked about this last time, if these are average weight losses on two different diets, you could say one diet, people lost on average 10 pounds more. So that would be saying that the difference mu1 minus mu2 is 10 pounds. So there's no reason that this difference has to be 0, but that's just what we do because we do it. We have mu1 equal to mu2 because it's easiest. But it sort of limits it. You know, you don't have to worry about any other weird cases coming up in the homework. But I'm just saying it doesn't have to be this simple. You can make it more complicated. You can always make things more complicated. H1 has 3 versions. So as you know, mu1 less than mu2, mu1 greater than mu2, or mu1 not equal to mu2. And of course, this is the left tail test, the right tail test, and the two-tail test. Okay, so now for this example, obviously we're going to say mu1 is equal to mu2, so that in general, what we're saying is there's no real difference in terms of the average amount of hours that kids sleep, regardless of how much TV they watch. That to me is not logical, but that's the null hypothesis. And of course, we have different amounts in our sample data, 6.78 hours versus 7.44, but we're just saying that that difference that does exist here is not statistically significant. So you would not be able to, if that's true, then you would not be able to reject the claim that the population means are equal. Okay, now, remember the first group given is the people who are watching, sorry, the first group given are the kids that are watching 3 hours or more of TV. The second group is less than 3 hours. Okay, so what are they claiming for our alternative hypothesis? Anybody?
That mu2 is less than mu1.
Now, mu2 is the group that watches less TV. We're counting how many hours of sleep they get. So do you want those kids watching less TV to have more sleep or less sleep?
I'm kind of confused.
The kids that watch TV, are they getting more or less sleep? They watch too much TV, are they getting more or less sleep?
Less sleep.
Right. So what we're saying, and the thing is they're the first group that's mentioned. So mu1, these are the kids with more TV. Okay, mu2 is the kids with less TV. But we're not talking about how much TV they're watching, right? We're talking about how much sleep they get. So we're saying the mean with the kids with more TV, the mean amount of sleep should be less than mu2. Does that make sense?
Yes.
Okay, so this is a left tail test. And it's tricky, right? You want to set this up so that this is what determines your p-value. Okay.
Professor, is the hypothesis A or 1 on the second sample?
Oh, yeah, you got me. Thank you. It takes me a little time to shift gears for the rest of the week where I use HA. Thank you for that. All right, so next we have to compute our test statistic. So as we said, this is a T statistic because you don't have the two population standard deviations and you're using sample standard deviations, which causes more variability in the possible outcomes, just more uncertainty, a different probability distribution. So let's go ahead and give the formula for the test, for our test stat. T is, as we've, I've just never written it as T before. Is the only real difference here. And I'll use the sample standard deviations. Sort of like that. Okay, we can go ahead and do this. So our X bar 1, 6.78 minus X bar 2, that's 7.44. You remember we assume the null hypothesis is true. So when it says mu1 minus mu2, we don't know what the values are, but the null hypothesis says whatever they are, they're equal. So when you subtract them, you should get 0. So you're always kind of saying minus 0 in that numerator when you do these two population tests. Okay, and that doesn't even need to be, this mu1 minus mu2 doesn't really need to be in the formula, except we're saying, well, technically you could say, that the difference is 10 years or something like that. Okay, so then in the denominator, the standard deviations were 0.63. And that's over 14 plus the other variance 1.05 squared over its sample size, which is 18. Okay, guys, so why don't you try and do this computation? Does anybody want to see me do this in Desmos? This is a kind of an ugly one.
Yes, please.
Okay, let me pop over there real quick. Okay, so here's Desmos. Let me go into it. I think when I build a fraction these days in Desmos, I start by just doing the slash for divided by. Okay, and so if you just do the slash to start with, it builds up a nice fraction for you. So 6.78 minus 7.44. No point in putting minus 0 up there. Now the square root is inside the toolbar that you pull up from the bottom. The square root key there. Now I need another fraction, so I'm typing slash. And then 0.63 to the second. Okay, any questions about anything? Over 14. What I like about Desmos is if it looks right, you know it's the right answer. Another fraction, so I hit slash. 1.05. This is also squared. And then its denominator is 18. Now this should all be inside of one square root. If anything, if you look at it and it looks like that square root bar doesn't go across the whole denominator, then you've made a mistake. Okay, so does anybody have any question about that computation? I'm gonna write it as negative 2.205. A little bit maybe overly precise, but that's fine. I'll round when I'm done, maybe. Okay, any questions here? Okay, and then the degrees of freedom are the complicated part. So just to remind you again, the problem. Oh wait, I got to go back to my iPad. Hang on. Okay, so there's our T statistic. And then just to remind you of the problem here, there's two different sample sizes. We used to use always n-1 for the degrees of freedom, but there's two different n's. There's an n1 and an n2. Now, if you look at the 13 degrees of freedom in the first one and the 17 degrees of freedom in the second one, 13 and 17 is 30. So in fact, the degrees of freedom are going to be pretty close to 30, but it won't be exactly 30. There's a couple of researchers that did a lot of work to create this test it's called the Smith-Satterthwaite test. That's what the nerdy books call it. They're all nerdy, but some of the nerdier books, I guess. And so the Smith-Satterthwaite test basically has a way of combining the degrees of freedom that still preserves the distribution as a T distribution. So here's a formula. I'm going to do in the numerator a V1 plus, I'll tell you what V1 and V2 are in a sec. V1 plus V2, that quantity is squared. In the denominator, it's over V1 squared over N1 minus 1 plus V2 squared over N2 minus 1. Okay, isn't that beautiful? And so V1 is the variance of the sample means from population 1. So that's S1 squared over N1. And V2 is S2 squared over N2. Okay, So you have to compute those first before you can do the degrees of freedom. All right, so the S1, let me go back up here. And it's funny because you can actually just copy the S1 squared over N1 is just this thing here. Okay, so you've actually sort of computed it already, but I'm just gonna copy and paste that down. And then the S2 squared over N2 is this part. So I'll copy and paste that down. Now the problem with this formula is that it's kind of sensitive to rounding, which is another way of saying people who do it right but round just a little differently, sometimes they get really different answers even though there's no mistakes. And that's always a headache. So generally what I'll do on an exam is I'll just tell you what the degrees of freedom are on this one so that you don't have to, so I don't have everybody getting a different answer. But in the homework, you have to compute it. Personally, I would just look it up for the odds, but on the evens, you'll have to compute it. Okay. Anyway, so, and the trick is to not round this too much. So, you know, I'm going to pop over to Desmos real quick here. I'm not going to show you anything yet because I'd be going back and forth. So I don't want to do that. Well, actually, I'll show you. Because I'll just show you how I'm going to handle this. Okay, so I think I'm going to call the first, there's a V1 and a V2. The problem is you have to do subscripts if you're going to do a V1 and a V2. If you do V and then you do the underbar character, it'll let you do a subscript. So the underbar is a shift on the minus key. So if you hold shift and press minus, you get a subscript, and so a V1, and then you have to press the right arrow to get away from that subscript. I'll just say V1 equals, and then I'm just going to copy and paste the way I did in the notes from the above expression. There. So there's V1, and I haven't rounded it. And that's kind of the key. Now again, if I type V and then I do shift minus, it gives a subscript. So V2, and you can call these A and B if you like, if you don't want to use the subscripts. Can't call them both V because those would be the same thing. So V2, again, I'm copying and pasting this expression in the variance. So copy, paste, there's V2. And now all I'm going to do is I'm just going to type the formula for the degrees of freedom. So the formula has a fraction. And in parentheses, it's V1 plus V2. You have to leave those subscripts. Don't keep your cursor in the subscript or it'll type the parentheses in the subscript. Then close parentheses, and then this thing gets squared. I have a problem. Somehow I typed something bad. There we go, squared over. Now I have to do a V sub 1, leave the subscript, and then do a square and leave that, and you type slash, and it's over N1 minus 1, which is 13. Okay, and then leave that denominator and plus another fraction. This one's going to have a V sub 2, leave the subscript and square it. And it's over N2, which is 17. So there's the degrees of freedom. Pretty close to 30. Like I said, it's 28. You're technically supposed to round this to a higher number. So let me go ahead and, does anybody want to ask any questions about how I did what I just did?
Is that in the bottom there? Is that n minus 1 or is that n?
Yeah, no, you can see what n is up here. So n is 14, that's n1 is 14 and n2 is 18. And this formula requires N1 minus 1, which is 13, and N2 minus 1, which is 17. It's easier just to type that, just to put in. If you want me to be real precise, or even more clear, I'd say 14 minus 1 down there and 18 minus 1. So if that helps. Like
Yeah.
that. Okay, so at this point, let's go ahead and I'm going to fill in some of this. So it was, well, before I do though, any other questions from Desmos? Again, I'll just provide the degrees of freedom. You're supposed to round this one up, so on the exam, I'll just say it's 29 degrees of freedom. Okay. It says 28.4, but again, you round it up to 29. Okay, I'll give a brief explanation for why we do that in a second. Any questions? Okay. Okay, so the V1, hang on, I'm gonna go back, look at Desmos here. So V1 was 0.02835. V2, 0.06125. Okay, and then DF, so here goes 0.02835 plus 0.06125, that's squared. And then down below, 0.2835 squared over N1 minus 1, that'll be 14 minus 1, plus 0.06125 squared over N2 minus 1, which is 18 minus 1. Okay, and this comes out to 28, I'll just say 28.42. So you want to round this up to a larger number. But the key word is round up, and I should say to a whole number. But up is the key word only because it's a little complicated, but you end up, if you round down, you make the p-value smaller, which makes it more statistically significant, which makes it easier to reject the null hypothesis. And we don't want it to be easier to reject the null hypothesis. We want it to be hard. So that's why that's basically the gist of this. So we're going to round this to 29. So degrees of freedom is 29. Okay, so that's it. Horrible, right? One thing you could do, everybody, is you could just leave this formula in Desmos while you're doing the homework. So I've typed it in once, but once it's in once, you can just keep pasting the new numbers into it for V1 and V2, so you don't have to keep retyping that. And then the Desmos sheet will just automatically recalculate the formula when you change the inputs. So that's kind of a handy way to do it without making yourself crazy. You just got to do it once, or leave this. If you've already done it, then leave it open and wait till you get to it. Again, you won't have to do that on an exam. Okay, so now we're going to do our p-value. Again, it's 29 degrees of freedom. So put a little t here. Our statistic was negative 2.205, so it's on the left. Test statistic. Oops. So here's our p-value. Okay, and let's go ahead and look at table A3. So for degrees of freedom, you want to go this way to 29. Don't subtract 1 here. You've already computed the degrees of freedom. And for your t statistic, we'll go down to negative 2.2. Okay. So that's table for table A3. I don't think I have this here. So unfortunately, you're going to have to look at the notes for chapter 7 to see this table. So let's see if I've got this here. I don't know what I've got. So unfortunately, I'm going to have to leave this note. Negative 2.2 and 29. I think I can remember that. Okay. Gonna do the negative page. I think we can see it all just like that. So negative 2.2 is right here. 29 is way over there. So I'm just going to go all the way down to the end here at 29 degrees of freedom. Okay, is there any question about what I did just now for the t distribution? Again, these are p-values. The table says it. It's t distribution p-values. So you can, if you know it's t, then you know to use this table for your p-value. Okay, any questions? We're going to use 0.0180 for that. Trying to get my iPad to react to my commands. It's not working right now. It's kind of ridiculous. Okay, 0.0180. Okay, any questions? And I don't know what our alpha is, so I don't know what the conclusion is. It says 4% significance weirdly up here. So that's our alpha. So here we'll say the p-value is 0.0180, which is less than 0.04. That's our alpha level of significance. Okay, and as always, less here means that we reject the null hypothesis. And support HA, which had said mu1 is less than mu2. So this is, it's just saying the difference between these two groups of kids isn't just a random thing. It's statistically significant. It's just really unlikely to be a random kind of a chance difference. Okay, any questions about this? So we can wrap it up. The data support the claim. Support, ugh. Oh my goodness. Okay, is there any question? I think there's another one here. Let's just go through it real quick. Last call for questions on this one. Okay, so this one, there's no scaffolding. So scaffolding is where I just walk you through it like this. Then on an exam, of course, you don't get scaffolding. So this is unscaffolded. Let's go through this. Okay, so it says an instructor takes a random sample of 40 on-site students and 35 online students. She finds the final exam score for each student in the random sample. The mean score for on-site students is 75 with a standard deviation of 12. The mean score for online students is 72 with a standard deviation of 15. Conduct a test at 5% significance level to determine if the mean score for on-site students is higher than the mean score for online students. So again, we're going to zip through this. Our sample data are, okay, so for on-site, the mean is 75. I'll call that X bar 1. Standard deviation is 12. And the sample size is 40. Okay, which is bigger than 30. And I'll put a little check there. Okay, then online, and this is N1. So online students, X bar 2 is 72. S2 is 15. N2 sample size is up here, it's 35. Okay, this is also bigger than 30. So a little check mark. I think that's all you need really to do to show me that you've checked. You do need to kind of make it clear to me that you've checked somehow. If you just say greater than 30 with a check mark, and then we're both happy. Okay. We do have an alpha here of 0.05. Okay, null hypothesis is always going to be mu1 equals mu2. Now the alternative here, they're saying that the on-site students, those are students who are in physical classrooms, that they get higher scores on average. So you're saying that mu1 is bigger than mu2. Now, again, you do have a higher average, but remember, this is only from 40 students. So just because your 75 is bigger than 72, doesn't mean that's not a random thing. They're going to be different, right? So we expect them to be different just because of randomness. The question is it so significantly greater that it can't be due to randomness? Okay, so I think we're good here. Let's go ahead and do our T statistic. You guys interrupt me anytime you have a question. Now, I'm sort of tempted just to go over to Desmos and change my inputs there. So I'm going to do that. If anybody needs me to show it, let me know. But I'm just going back to that old Desmos page and I'm just changing all the numbers, but leaving the rest of it alone. Okay, so this time, does anybody have this?
I got 0.949. But I'm
Yeah,
not sure.
we're really close. Let's just say 0.95. I have a slightly different third digit, so one of us did something differently. Well, I'm checking my numbers here. 12, 15, 40, 35, 75, 72. Because I got 947.
Yeah, me too.
Okay. I'm gonna go, since that's confirmed, I'm gonna go with the 947.
Okay.
And I just say you could check your numbers. You're really close. So there's just a small thing. Okay, now again, to get the degrees of freedom, now that's a really, by the way, that's a really small t statistic. That's not going to be statistically significant. You're basically saying these two means are less than one standard deviation apart. That's a normal deviation. Why would that indicate statistical significance? It's a normal deviation when there is no, when the null hypothesis is true. When the population means are equal, we expect the sample means to be a standard deviation apart because that's how randomness works. It's an average normal deviation. We're looking for the sort of the abnormal deviations. Okay. Any questions? So I'm going to put my 0.947 real close to 0 this time.
So
then,
at this point, we were trying to find the degrees of freedom, right?
well, unfortunately, yeah, I actually forgot about it. Okay, so, but again, I'm just going to paste the 12 squared over 40 in for V1. I'll write this down in a second. But I'm back in Desmos, just pasting the 12 square over 40 in for V1 and the 15 squared over 35 into V2. So I've already got those. And I also believe something is wrong. V1 is 3.6, V2 is 6.43. I don't understand how in the world my degrees of freedom didn't change. Oh, because I didn't change the sample sizes. 40. And 35. Okay. Yeah. All right, so let me write down what we get here for the degrees of freedom. So for my V1, this is going to be S1 squared over N1. My V2 is S2 squared over N2. And so those will be the 12 squared over 40 and the 15 square over 35. Now, I kept a lot of precision on this and they're rounded, at least V1 is just 3.6, but the V2 is a bit of a mess. It's 6.4288, 6.4286. Okay, so the degrees of freedom formula is this. If you ever ask me where's that formula come from, I will look at you and say, I have no idea. This is the only formula I have never, ever bothered to learn where it comes from. I'm ashamed to admit it. I should know. 6.4286 squared. I just figured, okay, these people who figured it out are geniuses. I probably don't understand what they did. That's what I'm thinking. Okay, so this is coming out. Did anybody get this? So I'll tell you what I got, and let's see if anybody disagrees. I got 64.98-ish, which of course we're going to make 65. I hope is right.
I got 64.977.
Yeah. Yeah, 977, right?
Yes.
So yeah, we're together on that. Good. Okay, so we're gonna use,
Professor, I got 976. So I just rounded it off wrong.
no, you're fine.
Okay.
Let's leave it. Let's let it go. That's gonna be
Okay.
rounding in the V1 or the V2, so that's fine.
Got it.
So we're gonna say 65, whatever you're saying, we're gonna say 65 degrees of freedom there. So for our p-value, now, no, again, normally you would do table A3 for this, which is the t distribution p-values, and the degrees of freedom, you would go out to 65. The t statistic, you would go down to 0.9, which is, I guess, how you'd have to round that. So it's zero, you just have to do 0.9 there, okay? And I'll go ahead and look it up real quick. 0.9 and 65. So you're not going to be able to do it because 65 is not in there. Okay, so I'm popping back to the chapter 7 notes real quick, just to bring that table up. Okay, and these are positive. So I'm just going to use 0.9, which is right here. And then for my degrees of freedom, again, it's 65. I guess we'll have to use 60. It was really, I don't know. I don't know whether to use 60 or 70. Let's just use 60. And so I think theoretically we should always round these up to a larger number, but on the exam, I always make sure that it's exactly on the test so you don't have to round. At least that's my goal, to make sure you don't have to round your degrees of freedom. Anyway, 0.8141. Remember, this is a right tail test. These tables give areas to the left. If you look at what I'm circling right here, these are areas to the left. Okay, so we have a right tail test. Let me go. Oh, I did not mean to do that. Yes, I did. 8141. So I'm trying to get, my iPad is just like killing me today. Okay, 0.8141, and that's the area to the left. So in the notes, I'll put that 0.8141 on the left, but our p-value will be 1 minus that. So whatever that is. Anybody get 0.186? I think I did something wrong. Okay, 0.1859 is better. Okay, any questions there? And I think yeah.
I kind of have a big picture question. So like in chapter 8, we use degrees of freedom because we are doing differences, right?
No. Degrees of freedom come up with whenever you are using sample standard deviations instead of population standard deviations here. These formulas are supposed to have the population standard deviations in the denominator. And if they do have the population standard deviations, then it's a Z statistic. So I'd have to refer you back to the original. Right, where is it? Right here. Nope. Here. Notice I have, in this form, I have this is the test we're doing right here.
Yeah.
But this has a population standard deviations. The second you don't have those and you put sample standard deviations in, you've got a statistic that will vary more because the sample standard deviations are going to change every time you do it. So this creates more uncertainty in what the possible values are for the statistic. So if you're using S1 and S2 here, this becomes a t distribution. sample standard deviations are what cause t-distributions. So we did that in chapter 7 and we're doing it in chapter 8. Okay, is that okay?
Yeah. All right. Thank you.
Yeah, it's whenever the the population standard deviations are not known, you'll see us using a t-distribution. Okay, almost done here. The p-value is kind of huge. So, oh, and there's one other thing before I get going there. Let me come back to my Canvas page here. I'm going to be sorry I did that. Okay. So I'm going to share my Canvas page. And just to remind you, under modules, there's p-value calculators for all the problems. So if I go into modules, there's a module called important bits here. And inside of there are the p-value calculators. If you just click on that, we're doing students t-distribution right now. That's the name of it, t. So if you click on that, just dial in your degrees of freedom. So this time it was 65. And then put in your t statistic, which was 0.947. This is way more precise because you don't have to round these. Okay, and you can see the better t value is actually, sorry, the area of the tail here is given, and that's your p-value on this one. 0.174 is better than what we're using. We're using 0.185. So it's like a 1 percentage point difference. Okay, so you're welcome to use this on the exam, and I'll make sure when I write it that I'll accept either answer, whether you do it from the table or from these t-distribution calculators. And there's all the probability distributions. I'm going to go back a page now. All the probability distributions, the normals distribution, you can do p-values on this link on the top. T-distribution you've seen repeatedly, and then before it's all over, there's going to be 2 more. Okay, so all the p-value calculators, again, it's under modules. In the module called important bits. The very first thing is the p-value calculators. Okay, any questions? You can use that on the exam. You don't have to use tables at all if you don't want. And I think I mean for p-values is what I'm saying. It's easier to use tables for critical values in general. So anyway, any questions? I'm going with this p-value of 0.1859 since that's how I started. It's wrong, but we're going with it. This is much bigger than the alpha, I think, which was 0.05, right? Yeah, 0.05. That's our alpha. So larger means that we don't get to support the alternative hypothesis because we're failing to reject the null hypothesis. So we don't support the alternative. H1, which had said that the kids in on-site courses are getting higher averages than the online students. We can't support that, not with these data. Doesn't make it not true, but we have no evidence to say that students are doing better in the online, sorry, in the on-site classes. Okay. All right, so the data, it's always about the data. They do not support the claim that the mean score for on-site students is greater than for online students. Okay, it might be, but we just don't have evidence. So I'm sort of hedging because I my own experience is that online classes don't go as well. But that's just my experience. Okay, how are we doing for time? It is 9:48. Let's go ahead and take a break. So 48. So let's take a break till 10 a.m.